In this video, we're going to look at sequences, and we're going to determine if it converges or diverges. We're going to calculate the limit of a sequence if it exists. So we're going to do a little bit of refreshing about sequences and series. So a sequence is just a formula that asking you to list out the numbers, and a series is the summation of a certain set of numbers. We're going to take a look at our first example. This is a recursive sequence. And the reason I know it's recursive is because this a sub n minus 1, it tells me that I need to know the previous term to find this term. So they're asking me to find the first four terms. So my first term, a sub 1, is given to me, that's 9. A sub 2, based on this formula, is going to be 3 multiplied by my previous term, which is 9 minus 20. And then a sub 3. Well, I need to know what a sub 2 is before I can find a sub 3. So this is going to be 27 minus 20, which is 7. So a sub 3 is going to be 3 multiplied by my previous term minus 20. To find a sub 4, I'll need to know what a sub 3 is. So it's going to be 21 minus 20, which is 1. So this is going to be 3 multiplied by 1 minus 20, which ends up becoming negative 19. So my sequence as a list would be 9, 7, 1, and 19. This represents a sub 1, this represents a sub 2, this represents a sub 3, and this represents a sub 4. That's a recursive sequence because it is required to know the previous number before I can get to the next number in the sequence. On these, they're asking me to, again, find the first four numbers of the given sequence. And this one does not require the previous equation. So I could jump to the 10th term if I want to. But they're only asking for the first four numbers of the sequence. So a sub 1 is going to be negative 3 multiplied by 1 plus 8. A sub 2 is going to be negative 3 multiplied by 2 plus 8. And then a sub 3 would be negative 3 multiplied by 3 plus 8, and then a sub 4 would be negative 3 multiplied by 4 plus 8. Now the assumption is, unless stated otherwise, that we always start out with n being 1, because n usually represents a natural number. When we get further in, though, we're actually going to start with n equals 0, but for this we're going to assume that we're going to start with n equals 1. So then my first one would be 5. That's a sub 1. My a sub 2 is going to be 2. My a sub 3 is going to be negative 1. And my a sub 4 is going to be negative 4. So when I put in a sub 1, when I put 1 into this explicit or closed formula, I get 1 out. When I put in 2, I get 2 out. When I put in 3, I get negative 1 out, and when I put in 4, I get 4 out. When it's not a recursive sequence, then if they wanted me to find the 10th term, a sub 10, it is simply putting in the 10 into wherever I see my n. My next example is an alternating, and I know it's alternating because of this negative 1 right there. So let's go ahead and start out with d sub 1, which means I'm going to put negative 1 wherever I see n. I'm going to put in 1, so 1 squared over 1 plus 1. And d sub 2 is going to be negative 1 squared, 2 squared, and then 2 plus 1. D sub 3 will be negative 1 raised to the third power, 3 squared, and then 3 plus 1. And then d sub 4 would be negative 1 raised to the fourth power, 4 squared over 4 plus 1. So my first term in the sequence would be negative 1 multiplied by 1, which is negative 1 divided by 2, so negative 1/2. My second term in the sequence would be negative 1 squared, which is positive 1, multiplied by 2, which is 4, divided by 3, so 4/3. My next term in the sequence is going to be negative 3 raised to the third power, which is going to give me a negative number. And then 3 squared is 9, so negative 9 over 4. And then my last one that they're asking me to find, because they only want my first 4 terms, is that it would be -1 to the 4th, which is 1, and then 4 squared, which is 16 divided by 5. Again, a sub 1, a sub 2, a sub 3, and a sub 4. When we look at the next example, this is slightly different notation, but it's still assuming that we're going to start with n equals 1, and it's actually telling us explicitly we're going to start with n equals 1. Each one of these closed or explicit formulas assume that this sequence will go on to infinity. This one is telling explicitly that it will. So we start out with our, I'll do this in green maybe, I'll do it in black. A sub 1, which will be the natural log of 1 divided by 1. A sub 2, which will be the natural log of 2 divided by 2. A sub 3, the natural log of 3 divided by 3. And a sub 4, which is the natural log of 4 divided by 4. Let me just erase this so I can have the space. And so the natural log of 1 is 0, so my first term happens to be 0. And then it's 1/2 the natural log of 2. And I can find a decimal equivalent, or I can leave it. I'm just going to leave it. And then I have 1/3 the natural log of 3, and then 1/4 the natural log of 4. So these are my first 4 terms, were a sub 1, a sub 2, a sub 3, and a sub 4. If we're asked to find a closed formula or an explicit formula for an arithmetic or a geometric sequence, these are the 2 equations that we can use. Now this may be slightly different from what you've seen in the past, but it's totally okay. It'll work out the same way. The one you probably may have seen is a sub 1 plus dn minus 1. Now, totally okay if you've seen it this way. It ends up cleaning up to that there. Use whichever one makes you happy. Now, if you're trying to determine whether or not it is an arithmetic or a geometric, then this is what must happen. If it is an arithmetic, then the difference between the terms must be the same. If it's a geometric, then the ratio must be the same. Terms. In particular, a sub 2 divided by a sub 1 must be the same as a sub 3 divided by a sub 2, which must be equal to a sub n plus 1 divided by a sub n. And this is where the r, the ratio is, and that's what that r comes from. This d comes from the difference between them. So if I go back to my first 2 equations here, if I wasn't given that equation and I was just given my list of numbers, then I would look to my list of numbers, and the first thing I always do is see whether or not that I have the common difference between them. So I take a look at this and I say, oh, 2 minus 5, that's -3. -1 minus 2 is -3. -4 minus -1 is -3. And there's my distance between them, or the difference between them. And then from there I could find my 8. I must have had, starting with a sub naught, well, we should probably tell you what a sub naught is. A sub naught for this, as I said earlier, this is the previous one of the equations I gave you that I erased. A sub naught is going to be a sub 1 minus my difference. So my a sub 1 was 5. So my a sub naught on this example would have been 5 minus a -3, which is where this 8 comes from. All right. So then my geometric. Now, if I look at my first three terms, which of course I erased on D, my first four terms, I had negative 1/2, and then I had 4/3, and then I had negative 9/4, and then the next one was 16/5. Now, let's see if this is a geometric. So I can tell you that the difference is not the same between them, just by looking at it. So for the geometric to work, I must have 4/3 divided by negative 1/2, which ends up being 4/3 multiplied by negative 2/1, which gives me negative 8/3. That must be the same thing as negative 9/4 divided by 4 divided by 3, which is negative 9/4, multiplied by 3/4, which we can see is not going to give us the same value. This gives me negative 27/16. And these are not equivalent, so this is not geometric, but this one is arithmetic. So here's some more examples in which I'm going to determine it just like I did up above. So the first thing I always do is look to see if I have a difference between them. It is 10 minus 5, which is 5. So I'm going up 5 each time so that we know that this is arithmetic. My difference is 5. So my a sub n, I'm going to use a sub naught plus dn. So I have to find my a sub naught. This is going to be my a sub 1 minus my difference. My difference is 5. So my a sub naught must be 5 minus 5, which is 0. So my a sub n is going to be 0 plus d times n. So that's my closed sequence, my closed formula. Let's take a look at my next one here. I have 100. So I can see by glancing at it, it's not going to have the same ratio or the same difference between them. So let's see if we have the same ratio. So we have 20/100. We ask ourselves, is that the same thing as 4/20? And then we ask ourselves, is that the same thing as 4/5/4? Well, and 4/1. Let's do some reductions here. 20 goes into 100 1 out of 5 times, so that's 1/5. 4 goes into 20 1/5, so that seems to be holding. And then we look to our last one. This 4/5 multiplied by the reciprocal 1/4, which gives me 1/5. So this is 1/5, and so this is geometric. Now with geometric, we haven't done the closed formula for that. The closed formula based on this is going to be a sub n is equal to my a sub 1, which is 100, and then my r, and my ratio here is 1/5 raised to the n minus 1. And so that's my closed formula. And this was my closed formula. Where did I put that? I must have erased it. A sub n is equal to 5n. Okay, let's take a look at my next example here. On my next example, I have 70 minus 75 and then 80. So I'm going to ignore the alternating part because I see that it's alternating. So I'm going to have a negative 1 as part of my alternating sequence. So if I just have 70, 75, 80, 85, 90, etc., if I ignore the negative, know that I'm going to have an alternating series, then I can see that I'm going up 5 each time. So plus 5, plus 5, plus 5. That means my D is 5. My A sub naught would be 70 minus 5, which is 65. So my closed formula, A sub n, is equal to, I'm going to leave a little space here. It's going to be my A sub naught, which is 65 plus 5 times n. Now, the alternating sequence is I'm going to put a negative here. Now I'm going to figure out whether I want the first one positive or the first one negative. If I want my first term to be positive, when I put in 1, I better make this as n plus 1. If I would have had a negative here, then I would have just had an n right here. But since my first term is positive, my n plus 1 is going to ensure my first term is positive, my second term is negative. Now this is something a little different. They're like, well, what? Basically, each one of these are my outputs. In fact, my sequence is -3, -1, 1, 3, and 5. So that's actually my sequence. So looking at this, to go from here to here, I must have +2, +2, +2, and +2. Therefore, I have D is equal to 2. My A sub naught is going to be -3 minus 2, which is -5. So my closed or explicit formula is going to be -5 plus 2n, and there is that one. Now I know a lot of this is review for you, and if it's not, that's okay too. Please ask questions in class on any of this stuff, because this will be foundational work for what we're going to finish up in chapters 5 and 6. We want to find the explicit formula for the nth term of the sequence. Oh, isn't that what I'm supposed to be doing here? Oh, no, I wouldn't. I gave you more than you needed. That's okay. So taking a look at A, this goes up by 20, this goes up by 20, my D is 20, my A sub naught is going to be 40 minus my 20, which is 20, my A sub n is going to be equal to 20 plus 20n, and if I wanted to, I could do 20 1 plus n if I'm inclined, because I have the 20 as part of both of them. Okay, so let's take a look at the next one. And this goes up by 1, this goes up by 2, this goes up by 4. Okay, not arithmetic, so let's look if the ratios hold. 2 to 1, 4 to 2, 8 to 4, 16 to 8. So this is a ratio of 2. They all maintain the same ratio. So then this A sub n is my A sub 1, which is 1. So I don't have to write that if I don't want to. 2 to the n minus 1. So in other words, just 2 to the n minus 1. And that is my closed formula, just like over here and over here. So we take a look at C. It doesn't look like I am going down by the same amount, but I could be wrong. I'm going to write this as 2 over 1. And so then I would look to see what the difference is between 2 over 1. Oh, it's alternating. So I'm going to ignore the negative. So I'm going to write this as 2 over 1, 4 over 3, 8 over 9, 16 over 27. Oh. Huh. So, because I have fractions here, I'm inclined to approach the numerator separately than the denominator. I'm going to go ahead and find my ratios though, because it doesn't look like it's going to be an arithmetic. So if I look at my ratios, it would be 4/3 divided by 2 over 1, which is going to give me 4/3 multiplied by 1 over 2, which is 1 over 6. Now let's see if it holds for the second one, which is 8 over 9 divided by 4 over 3. So 8 over 9 multiplied by reciprocal, 3/4. This cancels here to be, oh, that should be, hello, make sure you know how to cancel correctly, and clearly I didn't. So this is 2/3. And then this cancels into 3, 1, 2, oh, it's 2/3. Oh. Well, look at that. It's a geometric. So then if this is the geometric, then my A sub naught is going to be my initial term, which is 2. I'm going to deal with a negative in a moment, so I'm just going to shove this over a little bit. So 2, that's my A sub 1. 2 to the third raised to the n minus 1. 2 divided by 3 raised to the n minus 1. Then I have the negative. I want my first term to be negative, so this is just going to be n. And so there's my geometric closed formula. And I take a look at D and I think, I've got x's in there. How am I going to deal with that? Well, it's alternating again. So let's write this without the negatives, and let's write this over 1. x cubed over 3, x to the 5th over 5, x to the 7th over 7. Huh. Well, what it looks like is that the ratio probably won't be the same, but let's check it. I can tell you the difference isn't going to be the same. So I know it's not arithmetic. I have x to the 3rd divided by 3 divided by x over 1. This is going to give me x to the 3rd divided by 3 multiplied by 1 over x. This gives me x squared over 3. Yeah, and I'm not even going to do the second one because I see that I'm going to have 5s and 3s that are not going to cancel themselves out. When this happens, this is neither geometric nor arithmetic, and that's okay. That doesn't mean we can't find a closed formula. If we approach the denominators separately than the numerators, I can see that I'm doing plus 2 here, plus 2 and plus 2. So it looks like the denominator is arithmetic. So it would be, my denominator would be d is equal to 2. A sub naught is going to be negative 1 minus 2, so negative 3. So my a sub n for my denominator is going to be negative 3 plus 2n. Oh, excuse me. I cannot obviously add today. Man. So this is negative 1 and this is negative 1. There we go. Okay. Now let's look at the numerator. The numerator, obviously I'm not adding x's, so let's look at the ratio. I have x to the 3rd divided by x. Is that the same thing as x to the 5th divided by x cubed? Is that the same thing as x to the 7th divided by x to the 5th? And the answer is yes. I have x raised to the 2 on each one of those. So, negative 1 raised to the n plus 1, because I need to have my first term positive, and then I need him to alternate. And then I have x squared as my ratio, raised to the n minus 1. I can clean this up just a little bit. I have negative 1 raised to the n minus 1. And I can write this as x raised to the 2n minus 2, negative 1 plus 2n. Let's take a look at my last example here. I'm going to write these all with 1 over 1, 1 over 1, 4 over 3, 2 over 1, and 16 over 5. Well, that didn't help me a lot. So let's see, make that a little better. Let's see what happens if I have it, looks like it may be 1, 2, 3, 4, 5. So I think what the bottom looks like is 1, 2, 3, 4, 5. That's my question. So I would need to make this to have a denominator of 2 is multiply numerator and denominator by 2. To have this as a denominator of 4, I'd need to multiply numerator and denominator by 4. So then my sequence would look like 1 over 1, 2 over 2, 4 over 3, 8 over 4, and 16 over 5. Now I know I don't have the same difference. I don't have the same ratio. So I think the way I'm going to approach this is I'm going to look at the numerator and the denominator separately again. This is going up by 1, right? We can see that's going up by 1, so my d is 1. My a sub naught would be 1 minus 1, which is 0. So my denominator, since it's arithmetic, would be just n. My numerator, these 2, 4, 6, 8, 16, these are factors of multiples of 2. 2 to the 1, 2 to the 0, 2 to the squared, 2 to the 3, 2 to the 4. So I know that my r is going to be 2. So this is going to be 2 raised to the n minus 1. And it is neither geometric or arithmetic, but the numerator is geometric and the denominator is arithmetic. So there was some examples of getting us prepared for looking at the limits of a sequence, which is really the meat of this chapter. So fundamental question that arises when we're looking at infinite sequences is how is this sequence going to behave as n gets larger? We're going to say that a sequence converges if the limit as n goes to infinity of my sequence becomes a particular number. If it is not convergent, then clearly it must be divergent. So in other words, I want to know what the behavior of my long-term sequence is. Does it go to a number or does it not? More formally, this is how we're going to define it. The sequence a sub n converges to a real number L if for some epsilon, and you're thinking, wow, I love epsilon. And I'm going to say, cool, I'm glad you do. Epsilon is greater than 0. There exists a number n such that a sub n minus L is less than epsilon if n is bigger than cap N. The number L is the limit of the sequence, and we write it in this manner. Because sequence is a function whose domain is a set of positive integers, we can use the property of limits to determine whether a sequence converges or not. So here's our first limits. So consider our first theorems, my first theorems. A sub n is equal to some function n for n greater than or equal to 1 as x approaches infinity of my function is equal to L, then when it converges. So in other words, we have the limit as n approaches infinity of a sub n is equal to L. Otherwise, it diverges. Here's some rules that we get with our algebraic limit laws where we have the two sequences where a sub n and b sub n are sequences. The limit of a sub n as n goes to infinity is a. The limit as n goes to infinity of b sub n is equal to b. Then these are the things that we get. We get the limit of a constant is a constant. If we have a constant times our sequence, we can pull the constant out, and it'll be the constant times a. Plus or minus, I can break them apart when appropriately. Multiplication, I can break them apart when appropriately. And division, of course, I can break them apart appropriately. So we're going to start out with some very basic, making sure that we've got our understanding. And we're not going to find limits yet. We're getting there. We're getting there. So we have the limit as n goes to infinity, and they tell us what the limit of a is and the limit of b sub n is. So using our rules up above, this is going to be 3, the limit as n goes to infinity of a sub n, minus 4, the limit as n goes to infinity of b sub n. So it's going to be 3 multiplied by 1 minus 4 multiplied by negative 1, which gives me 7. Now this one's a little bit more involved in the fact that I'm going to have to distribute the limit on the numerator and denominator and then do the subtraction and addition. So I have the limit as n goes to infinity of a sub n plus the limit as n goes to infinity of b sub n over the limit as n goes to infinity of a sub n minus the limit as n goes to infinity of b sub n. Now I used a bunch of stuff. I used this one and I used this one, so I used 2 different rules there. And now I can do the replacement as limit as n goes to infinity of a sub n. We know that's 1. And then plus the limit as n goes to infinity of b sub n, that's negative 1. And the denominator, I have 1 minus a negative 1. So I end up with a 0 over 1, which gives me just 0. Actually, 0 over 2. I cannot add today. I am sketchy. Gotta be paying attention because I'm sketchy. Okay. Now we're going to find the limit of each of the following sequences, and we're going to use L'Hopital's where it's appropriate. Again, if you remember, we have been working with L'Hopital's for a while, so we have to make sure that L'Hopital's applies. So what they're asking me to do now is actually find the limit. I don't know what it is. The limit as n goes to infinity of n squared over 2 to the n. Now I checked to see if this is one of my indeterminate L'Hopital's. As n goes to infinity, this goes to infinity, and this goes to infinity. So I can use L'Hopital's on this because it is one of my indeterminate forms of L'Hopital's. I'm not necessarily going to take the limit of each one individually like I did up above. So then this is just going to be equal to the limit as n goes to infinity. The derivative of the numerator is 2n. The derivative of the denominator is 2n, the natural log of 2. So now I'm going to do L'Hopital's probably again because I still have infinity over infinity. I can pull out 1 over the natural log of 2 because that's just a constant. So I have the limit as n goes to infinity of 2n over 2 to the n. Again, it's infinity over infinity, so I'm going to use L'Hopital's. So I have 1 over the natural log of 2, the limit, as n goes to infinity. I end up with the numerator of being just 2, and the denominator I have the 2 to the n, the natural log of 2. So again, I can pull out the 2 and the natural log of 2. So I have the natural log of 2, the quantity squared, the limit. And I didn't have to do that step. I'm just making it easier to realize that I have 1 over 2 to the n. Now, as n gets really, really large, I'm dividing by a very, very large number, which means that 1 over a very large number goes to 0. And so my final answer is going to be 0, because 0 multiplied by this constant is going to be 0 all day long. All right, let's take a look at this one. We're assuming that these are, of course, my closed formula. So I have the limit as n approaches infinity of n minus 1 squared over n plus 1 squared. So I ask myself, can I use L'Hopital's? And the answer is yes. So that's because as n gets really large, this is infinity and the denominator is infinity. So we know that this can be done by L'Hopital's. Simultaneously, if I'm like, yeah, I don't know if I want to use L'Hopital's, let's go ahead and expand these out. So I get n squared minus 2n plus 1 over n squared plus 2n plus 1. And we know back in calculus 1, we can divide each one of my terms by the highest power in the denominator. And when we do that, we end up with the limit as n goes to infinity of 1 minus 2 over n plus 1 over n squared over 1 plus 2 over n plus 1 over n squared. As n gets large, this goes to 0, and this goes to 0, and this goes to 0, and this goes to 0. So my answer is 1. Now, if I was asked to decide whether or not these converge or not, this is equal to 0. It's a number, so this converges. This is equal to 1, so this converges. Let's take a look at my next example here. So if I have the limit as n goes to infinity of n raised to the 1 over n. Now they're giving me a hint here. This is of the form, by the way, the indeterminate form of infinity raised to the 0. So we know that when we see that form, we have to do the L'Hopital's, but to do the L'Hopital's on this, we have to do y is equal to n raised to the 1 over n, take the natural log of both sides, so the natural log of y is equal to the natural log of n, 1 over n, so the natural log of y is equal to 1 over n, the natural log of n. That's where they're telling you, hey, look at that. And so if I'm asked to find the limit as n goes to infinity of the natural log of y, which is the same thing as the limit as n goes to infinity of natural log of n divided by n, this is infinity over infinity, so we can use L'Hopital's. So this is going to be the limit as n approaches infinity of 1 over n divided by 1, which we can do a direct substitution, which gives me 0. So that tells me the limit as n goes to infinity of the natural log of y is going to be equal to 0. Okay, how does that help me? Well, we go back here. This is going to be equal to e raised to the 0, which is 1, because I let y equal this. If I undo that y equals that, it's going to give me e raised to that power, which gives me just 0. E to the 0, which is 1. So this converges. Okay. Continuous functions defined on a convergence sequence. Here's another theorem. Consider the sequence a sub n, and suppose there exists a real number L, so that the sequence a sub n converges to L. Suppose that f is a continuous function at L, then there exists some integer L that is defined for this. So here's an example. And of course, we get the Squeeze Theorem. And you're thinking, holy smokes, I love the Squeeze Theorem. I'm glad it's back. And I'm going to say, yes, yes, it is. We're so excited about that. So we're going to use the Squeeze Theorem to determine if these converge or diverge. So this first one is going to be a whole lot of fun. And this Squeeze Theorem goes back to the way that we define this sine and cosine on the unit circle. So the first one, if it was just the sine of 1 over n, there's a lot more work to that than you'd like. So let's look at the Squeeze Theorem for this first one like we did in Calculus 1. So we have this triangle that's going to be built. Let's zoom in. Let's zoom in so I can give myself more space without needing more space. So let's redraw my unit circle. So here's my unit circle. I'm going to build a right triangle in which this is the angle 1 over n. Now, because this is a unit circle, this point is the x comma y, which on the unit circle is going to be the cosine of the angle, which is 1 over n, and then the sine of the angle, which is 1 over n. Which means this length, give or take, will be the sine of 1 over n. Now, this point out in space is going to be some point x comma y. Now, the tangent of 1 over n is defined as the y value over the x value. The x happens to be 1 because this is the unit circle. So the tangent of 1 over n is equal to y, and that's that length. So if we take a look, we have two triangles. We have first this triangle in yellow. We have this second triangle in red. And then we have this arc length in black, or the angle or the area of the sector. So what we're going to do now is using all of this information to be able to build the Squeeze Theorem. The area of the yellow triangle is going to be 1/2 the base, which is 1, times the height, which is the sine of 1 over n. That's going to be less than or equal to the area of the sector, which is 1/2, using my area of the sector formula, 1 over n, and then my radius squared, which is 1. And that's going to be less than or equal to my red triangle, which is going to be 1/2 my base of 1 and my height of the tangent of 1 over n. Now let's divide everything by, let's multiply everything by 2 first of all, so we can get rid of the fraction. And then simultaneously we're going to divide everything by the sine of 1 over n. So I get 1 is less than or equal to 1 over n, the sine of 1 over n, which is less than or equal to the tangent divided by the sine, which gives me the secant of 1 over n. So now I have my values, and let's go ahead and you think about, wait a minute, that doesn't match. That's okay. Don't panic. It's all good. Let's take the limit as n goes to infinity of 1, which is less than or equal to the limit as n goes to infinity of this 1 over 1 over n, the sine of 1 over n, which is less than or equal to the limit, the secant, the limit of the secant, the limit as n goes to infinity of the secant of 1 over n. Now, as the limit as n goes to infinity, on the first side it's going to be 1, which is less than or equal to this junk, which is less than or equal to the secant. Secant of 1 over n. As n goes to infinity, that's the secant of 0, which we know is going to be 1. So that means that middle piece has to be 1, which means that I have 1 is less than or equal to the limit as n goes to infinity of n, the sine of 1 over n, because if I take the reciprocal of all of these values, it's going to be less than or equal to 1. So we know this one goes to 1. So the answer is 1. Now I promise you that the other ones are not going to be nearly as bad as this one. Let's take a look at this a sub n. So we want to find one that's on one side and we want to find one on the other. So let's look at n factorial over n squared. Let's just write out some of these terms. So n factorial is n multiplied by n minus 1 multiplied by n minus 2 dot 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 all the way down to 1. My denominator is going to be n multiplied by n multiplied by n dot 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 n times. So this gets multiplied n times. So we know, erase this. We know that when we finally get done, this is going to be n over n multiplied by n minus 1 over n, just multiplied by n minus 2 over n dot 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 1 over n. Now, this becomes 1. This n minus 1 over n can be wrote as n over n minus 1 over n. This n over 2 can be wrote as n over n multiplied by 2 over n, or it's going to be minus 2 over n. And the next one all the way down to 1 over n. These cancel down to 1. So we end up with 1 minus 1 over n, 1 minus 2 over n, all the way down to 1 over n. Now this tells me that it must be less than, actually it's going to be strictly less than 1 over n. And the reason is that 1 minus 1 over n is going to be some number, and then I have this number which is going to be another fraction, and what's happening is my numerator fractions are decreasing, but my denominator fraction part is staying the same as n. That means that this has to be less than 1. But it's also greater than 0 because I have to choose n being 1, 2, 3. So n factorial over n raised to the n has to be greater than 0. Simultaneously, it has to be 1 over n. So when I take the limit, I know the limit as n goes to infinity of 0, which is less than the limit as n goes to infinity of n factorial over n to the n has to be less than or equal to the limit as n goes to infinity of 1 over n is going to be, when I get finally done, this is going to go to 0, so it converges. Let's take a look at my last example here. We have a sub n, which is sine 1 over n. What we know is that the absolute value of the sine of any angle theta has to be less than or equal to 1. So that tells me that the sine of 1 over n, the absolute value, has to be less than or equal to 1. And simultaneously, the sine of n, absolute value, has to be less than or equal to 1. Now we also know the limit as n approaches infinity of the sine of 1 over n is going to be 0, because as n gets really large, we're taking the sign of basically 0. The sign of 0 is 0 all day long. We bring all of this together and say the limit, well, actually, we'll start with this. The limit as n goes to infinity of, at the very minimum, is 0, which is less than or equal to the limit as n goes to infinity of the sine of n multiplied by the sine of 1 over n, which is less than or equal to the limit of the sine of the absolute value of the sine of 1 over n, because it's going to run between 1 and 1. Now, we know that as n goes to 0, the limit as n goes to infinity of 0, that's going to be 0, which is less than or equal to, which is less than or equal to, that junk in there. We know the limit as n goes to infinity of the sine of 1 over n, the absolute value, is going to go to 0. So that tells us our middle piece is going to go to 0. So the answer here is 0, and so it converges. We talk about bounded sequences. So a sequence is bounded above if there exists a real number m such that a sub n is never going to reach this number m for all positive integers n. We say it's bounded below if there's some number n such that this number is always going to be less than or equal to the sequence for all positive n's. It is, if the sequence is a bounded sequence, it's a bounded above and below. If the sequence is not bounded, we call it an unbounded sequence. Which then gives us, if a sequence converges, then it must be bounded. So, notice that a sequence being bounded is not sufficient for the sequence to converge. However, if it does converge, it is bounded, not the other way around. So we have a sequence is increasing if the outputs for each successive one is larger than the previous one. When I put in n equals 1, 2, 3 on up. It is decreasing if, for as I put in my n equals 1, 2, 3 on it, if the previous one was larger than the new one. And it's a monotone sequence if for all n greater than n naught, in other words, for all the next numbers that we look at, putting in n equals 1, 2, 3 on up, it's increasing for all of them, or it's always decreasing. So if it's always decreasing or always increasing, then we say it's a monotone sequence. The last one is convergence. If it is a monotone sequence, the monotone, if it's a bounded sequence, then there exists a positive number n sub naught such that a sub n is monotone for all n's bigger than n naught. Then we say that it converges. So let's take a look at some of the examples here to determine whether or not these are monotone, and if they're increasing, decreasing, and then of course whether or not these converge. So what I'm going to do is I'm going to start writing out some of the numbers starting with n equals 2. So I have 2 over 2 squared. I have 3 over 2 to the third. I have 4 over 2 to the fourth. I have 5 over 2 to the sixth. And for the next one, as I go on out, I would have some term that would be some a sub n plus 1. That would be my next term. I'd have my a sub n term. Actually, let me do my a sub n term, which is a sub n, and then I'd have some a sub n plus 1. Now my a sub n term is 2, or excuse me, n over 2 to the n. And then this one would be in the form of n plus 1 over 2 to the n plus 1. We can see that we can rewrite this nth term as n plus 1 over 2 to the n multiplied by 2. Now we're going to do some lovely but exciting algebraic manipulation. If I multiply the numerator by n, I don't know why I did that. If I multiply the numerator by n and the denominator by n, then I'm going to have n plus 1, 2 to the n, and then I'll have n over 2 to the n, 2 raised to the n. All I did here was I multiplied by n over n and then just rearranged it so that the 2 and the n went over the underneath as a denominator of n plus 1. And the reason I'm doing that is so that I can tell you that this then can be rewrote as n plus 1 divided by 2n, and then the n over 2 raised to the n is a sub n. Now, because I'm taking n, what number I have, larger than 2, so if I have 3 plus 1, which is 4, that is going to be less than 2 times 3, which is 6. So this fraction in and of itself is going to be a fraction that when I multiply by a sub n, because that fraction is less than 1, that tells me that that is going to be less than the actual a sub n. So this tells me that I am decreasing the entire time. So this sequence, which is n over 2 to the n, is decreasing the entire time. So it's a monotone. Now, the most I'm ever going to have is going to be 1/2. And the reason the most I'm ever going to have is because I am decreasing. So the largest number I'm ever going to have is this first term. So I'm bounded from above by 1/2, because that's this very first term. And I'm going to be bounded from below by 0 because I'm never going to get negative. I'm not ever going to have a negative number. So I'm bounded from below by 0. So that tells me my sequence is going to converge. I'm bounded from above and I'm bounded from below, and it's going to converge. Now let's take a look at my next example. We have the cosine of n squared. Just need to erase all of this. So with the cosine of n squared, we know that the cosine of any angle, theta, the absolute value, is going to be less than or equal to 1. That tells me that -1 is less than or equal to the cosine of any angle, which is less than or equal to 1, and theta is being any angle. The thing about sine and cosine is that if I have -1 is less than or equal to the cosine of n squared is less than or equal to 1, it's bounded, but it's not continuously decreasing or increasing. Cosine, it has the wave, a cosine wave. So this is going to oscillate between -1 and 1. And so even though it's bounded, it's not monotonic, so non-monotone, which, because it's bounded and not monotone, that means the series is divergent. Now let's take a look at my next example. I have n raised to the 1 over n. Okay. In general, that I'm going to have 1 plus x, which is a linear function, will be less than or equal to e raised to the x. Now you're thinking, how is that relating to what I've got here? Well, that's the general case. If I replace x with 1 over n, I have 1 plus 1 over n is less than or equal to e raised to the 1 over n. And you're thinking, okay, well, that's kind of close, but really not that close. Well, we know that this also simultaneously has to be less than or equal to e raised to the 1 over n raised to the natural log of n. It's the natural log of n, provided, of course, that we are looking at n greater than or equal to 3, will be a number greater than 1. So if I take any number, raise it to a power greater than 1, it's obviously larger than e raised to the 1 over n. So I'm going to make this a single fraction over here. So I have n plus 1 over n is less than or equal to e raised to the 1 over n, which is less than or equal to e raised to the 1 over n, the natural log of n. Which, that tells me I can drop out this middle term because the inequality still has to hold. So I have n plus 1 over n has to be less than or equal to e raised to the natural log of n raised to the 1 over n. Now we know by our laws of logs that this is going to be n plus 1 over n has to be less than or equal to n raised to the 1 over n. Now, n plus 1 over n is the same thing as n plus 1 multiplied by n raised to the negative 1, which is less than or equal to n raised to the 1 over n. Now let's multiply both sides by n. Again, n is a positive number, so it's not going to change the direction of the inequality, so the inequality will still hold. When I multiply both sides by n, I'm just going to have n plus 1, which is less than or equal to n raised to the 1 over n plus 1, which is n plus 1, which is less than or equal to n. I have 1 plus n over n, working with just the exponents. Now I'm going to raise both sides by 1 over 1 plus n, 1 over 1 plus n. So, and that's not going to change the direction of my inequality. So I have n plus 1 over 1 raised to the 1 plus n, which is less than or equal to n, raised to the 1 over n. But this is the definition, this left-hand side is the definition of a to the n plus 1. If this is n plus 1 would have been n plus 1 raised to the 1 over 1 plus n. But this is a sub n. So this tells me that this sequence is decreasing. So it's decreasing the entire time, so it's monotone. And we also know that it's going to be bounded below by 0 because this is never going to be equal to a negative number. So bounded below by 0. That means if we're decreasing the entire time, the highest number I'm going to have, so bounded above, is going to be my first term. The first value I can put in is 3. So I have 3 raised to the 1 over 3. So in other words, I have the cube root of 3. Because I'm bounded above and I'm bounded below, that tells me that this is going to converge. Now that we've kind of got an idea of how to determine if it's monotone and being bounded, let's actually find out if the sequences have a limit that shows if it converges or diverges. So our first example is the natural log of n squared over the natural log of 2n. So I'm going to take the limit as n approaches infinity of the natural log of n squared divided by the natural log of 2n. Now, I'm not asking for whether or not this is monotonic or not, if it's a monotone sequence that is increasing or decreasing. I'm just asking to decide whether or not it converges. I could look to see if it's going to be bounded, but just because it's bounded doesn't mean that it's going to converge, and just because it's unbounded doesn't necessarily mean it is going to diverge. So we look at our limit here, and this is one that we can just do L'Hopital's right out of the gate because I have it of the form of infinity over infinity. Because I can do L'Hopital's right out of the gate, the limit as n approaches infinity of 1 over n squared multiplied by 2n, and then 1 over 2n multiplied by 2. So I have the limit as n approaches infinity. This n will cancel with one of these n's. This 2 will cancel with this 2. So I have 2 over n over 1 over n, which then becomes the limit as n approaches infinity of 2 over n multiplied by n over 1, which gives me 2. So I have an actual number, so that tells me we converge, and we converge to the number 2. Now let's take a look at our next example. So this is one of those definitions that we're all supposed to remember, but probably don't. It's one I have to look up too. We have this definition of the limit as n goes to infinity of 1 plus a over n raised to the n is equal to e raised to the a. So this can be rewrote as 1 plus negative 2 over n raised to the n, which means when we take the limit as n approaches infinity of 1 plus negative 2 over n raised to the n, a is equal to negative 2, so then this converges to e raised to the negative 2, in other words, 1 over e squared. So it does converge, and it converges to 1 over e squared. This section of the book is going to have a whole bunch of stuff that we have forgot. Please ask questions. When you're looking at the homework, please ask the questions. When you're looking at what I'm doing here, please ask questions, because this is a lot of stuff that we have learned at one point and have totally mostly forgot. So please, please, please ask the questions. Look at my next example, and this is factorial, which we may or may not have spent a lot of time on factorial. What I'm going to do is I'm going to start writing out the factorial just to make my life a little bit easier, if at all possible. So n factorial squared is going to be n factorial multiplied by n factorial. Now in the denominator, I'm going to have 2n, 2n minus 1, 2n minus 2, 2n minus the n minus 1, and then I'm going to eventually have n factorial as well. And you're thinking, how did that happen? Well, let's look at 10 factorial. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 factorial. I'm just going to stop at 5 factorial. If I told you that this is 5, I'll do it this way. This is 2 times 5. 2 times 5 is 10 factorial. Then I'd have my first one, which is 2 times 5. My second one would be 2 times 5 minus 1. That's where 9 comes from. I'd have 2 times 5 minus 2. That's where 8 comes from. I have 2 times 5 minus 3. That's where 7 comes from. The next one would be 2 times 5 minus, and it would be minus 4. But I can also write this, instead of saying minus 4 to give me 6, right? Because that'll give me 6. Is I can write this one as 2 times 5 minus my n minus 1. Because 5 minus 1 is equal to 4. So that's where I get this term. And then, of course, the n factorial. The reason I stopped at this point is because I want to have the fact that I am going to have my n factorials cancel. So that's where it's coming from. All right, so then what this is equal to is n factorial is n multiplied by n minus 1, multiplied by n minus 2, and then all the way down to, if I keep scrolling down, I'll get down to 1. 2 to the n. I have 2 to the n minus 1, 2 to the n minus 2, 2 to the n. Well, let's clean this up. 2 to the n minus 1, n plus 1, distributing that negative through gives me n plus 1. So I'm going to get down to dot, 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 n plus 1. All right, so this then becomes, it's a multiplication. I can write this as n over 2 to the n multiplied by n minus 1 over 2 to the n minus 1 multiplied by n minus 2 over 2 to the n minus 2 all the way down to 1 over n plus 1. And you're like, well, what happens if you have more denominator values than you have numerator values? And that's okay, because you have a bunch of 1s in the numerator if you need them. You can just multiply by 1, so we can still break this up. That's okay. So now that we have broke it up in this form, then now I can finally take the limit. The limit as n approaches infinity is, I can take the limit of each one individually. So n over 2n multiplied by the limit as n goes to infinity of n minus 1 over 2n minus 1, and limit as n goes to infinity of n minus 2 over 2n minus 2, dot, 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 until I get down to the limit as n approaches infinity of 1 over n plus 1. This first one, as you can see, the n's will cancel and I just get 1/2. The second one, when I divide everything by my highest n in the denominator, which is n, we're using L'Hopital's, I get 1/2. This one also gives me 1/2. And then I get all the way down to this one, which gives me 0. Now I may get zeros before that, doesn't matter. A whole bunch of numbers times 0 is still 0. So this function does converge, and it converges to 0. So it converges to 0. All right, last example. We have a sub n is equal to the tangent inverse of n squared. And this one, I promise, isn't as bad, but it does take into consideration the domain of the inverse tangent and what its range is. So I'm just going to take the limit right out of the gate. The limit as n approaches infinity of the tangent inverse of n squared. Now, my direct substitution tells me I'm going to take the tangent inverse of infinity. Tangent inverse of x, its domain is negative infinity to infinity. Its range is non-inclusive negative pi over 2 to pi over 2. And that's because the shape of tangent. So tangent has vertical asymptotes at x is equal to pi halves and x is equal to negative pi halves. And this is what the tangent graph looks like. Now, if I am asked to evaluate the tangent inverse of negative or positive infinity, that means I must be approaching this vertical asymptote, which means my answer is simply pi over 2. So this one does converge, and it converges to pi over 2. That's it for this video. There's a lot going on, and there's a lot of refreshing of algebra and trig that you may have forgot. So please look through the examples. Look through the examples in your book and come with questions, especially if there's some nuance that you are not picking up on and you're not understanding each step, so that I can help you all out. You have a great day, and we'll see you in class.